Alright, hello everybody, and welcome to the Chapter 3, Quiz 3 Practice Problems for Scholars in Honors Chemistry. This quiz will be open notes, but it is still important to review the material, just because you can know what to expect. So, without further ado, let's get into our action. Match the subshell to the shape. Our s orbitals. S orbitals, that is when L equals 1. They are the most basic, so this one actually is the sphere. S for sphere, if that's an easy way to remember it. So the left image, the sphere. That's one that we are presenting as a s orbital. The p orbitals. P orbitals is the right image. The right image. The dumbbells. They kind of look like dumbbells, or two drops of liquid together. This is our, spell that. That is our p orbitals. P orbitals are when L equals 1, so they are the second L value, and they're a little bit more complicated than the sphere. Finally, our d orbitals are the middle image, which looks like a clover. Now, there are some of the d orbitals do look kind of weird. Let me space this out correctly while I type. But in general, the d orbitals kind of look like this clover, where there's 4 of these teardrops connected at the middle. All right. Suppose n equals 2. What are the possible quantum numbers for all electrons where n equals 2? Use this format here. So there is a doozy here. So I'm going to what I'm going to actually do is go over to a Paint document and kind of draw this in. Rather than type this in, that would not be easy. So I'm going to pull over a Paint document here. If we have n equals 2, we're going to have our L value. We're going to have our m sub L and our m sub S. So if n equals 2, this means that L can equal 1 or 0. So it's anything that is 0, 2, and minus 1. Because n is 2, n minus 1, 2 minus 1 equals 1. So L can be 1 or 0. So let's go with our first case where L equals 0. If L equals 0, then m sub L equals 0. There's no other options. It has to be 0. There's no positive or negative 0. And our m sub S can equal 1/2 or negative 1/2. This means it either spins upwards or it spins downwards. So we have this one right here. L equals 0. And m sub S equals negative 1/2. So this is our 2s orbitals, actually. I do want to create that connection too. Hopefully that will help create that connection. Because our n equals 2 and our L equals 0, these are the 2s orbitals. This one looks like a sphere. That's 2s. And there are 2 electrons that can fit in it. One that goes up and one that goes down. So we have our up and our down. Alright. I'm going to pull this over because we have a lot more to get through. Now, if L equals 1, then our m sub L can equal negative 1, 0, or positive 1. Because there can be 2 branching electrons in each one of these orbitals, there's a total of 6 of our 2p orbitals. This is our 2p orbitals. So I'm going to draw this. I'm going to draw all this rather than do it right here, and I will be back with that. Alright, so I have finished my drawing here. As we can see, all these have n equals 2. They all have L equals 1. These first two are in the first of our orbitals for our 2p orbitals. So we're going to draw it like this. These are the first two, the second two, and the third two. So we could even say this is the -1, this is the 0, and this is the +1. They each have 2 electrons in these orbitals, one that goes up and one that goes down. Alright, so total, these all are L equals 1. They are all p orbitals. They all look like, if we go back to here, they look like our dumbbells, right where my mouse is, but they are differentiated different axis. So this dumbbell is on the z-axis. Another one might be on this y-axis. Another one might be on this x-axis. So they are different in three-dimensional space. And each one of them can have 2 electrons in them. We call those electron pairs. So here is all of the n equals 2 electrons. And what I'm going to do now is actually copy and paste this image into the document. There we go. Alright, question 3. Which of the following sets of quantum numbers is illegal? A, B, C, or D? A. If n equals 2, L cannot equal 2. If n equals 2, then L must be 0 or 1. So our answer is going to be A. We already can know that just based off of this information. B is fine. This is a 3s orbital. Perfectly fine. C. This is a 2p orbital. And this is actually, if we look here, this exact combination is seen right here. That's C right there. And finally, D. This is also completely legal. If n equals 4, then L can equal 1 or 0, 1, 2, or 3. Any one of these. L is 3. If L equals 3, then M sub L can equal -3, -2, or well, can equal all that. Hold on. Let me make it in order just to be more clear. -1, 0, 1, 2, and 3. Right? So if L equals 3, then M sub L can be -2, and M sub S can be 1/2. That's one of the allowed states. So this is allowed, and this is allowed. The only thing that's not is A. So I will highlight this as our incorrect answer. Or as our correct answer. 4. How many total electrons can fit in each of the following orbitals? 2s, 3p, 3d, and 4f. So our 2s. So our 2s means that n equals 2 and L equals 0. If L equals 0, then our M sub L would equal only 0, which means we have just one orbital in our 2s, which can fit 2 electrons. I'm going to use 2e minus. 3p. With our 3p, we have n equals 3. Our L equals 1. And our M sub L can equal either 0, -1, or +1, which means you have 3 orbitals. 1, 2, and 3. The order doesn't really matter, which means you can have 1, 2, 3, 4, 5, 6 E minus in them. I'm going to clear our screen here. 3D. 3D means that our N equals 3, our L equals 2, which means that the M sub L equals -2, -1, 0, +1, and positive 2, which means there are 5 different orbitals in there, which we can fit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 electrons in the 3D orbital. Finally, for F, this means our N equals 4, our L is equal to 3, which means our M sub L equals -3, -2, -1, 0, 1, 2, and 3, which means there are 7 different orbitals, which you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons in them. And this holds true. The N does not matter. 3D and 4D will both hold 10 electrons. 4F and 5F will both hold 15. All that matters to calculate how many electrons are in the orbital is the subshell type, which is determined by the L number. Alright? So let's type this in. We can have 2 electrons in an S shell. We can have 6 in a P, 10 in a D orbital, and 14 in an F. Alright, so now we have a whole bunch of different examples. I'm going to pull this up so this is all on one page. I can't fit it. I'm going to fit this on. There we go. Alright, are the following electron configurations legal or illegal for a ground state? The keyword is ground state. Ground state means that there's no excitation, and this is what electrons will do naturally without energy. Alright, so this one, I'm going to figure out what's the best way to kind of draw this in. Be right back. Alright, so I'm going to go through and copy an image, basically. Our first one right here. This has electrons in 2s, but does not have an electron in the 1s. The 1s is a lower energy. It is closer to the nucleus. It is easier to get into. So already, this violates our Aufbau principle. So this is an illegal state. This atom, that's the wrong image. This work? No. There we go. There we go. Illegal. I'm leaving the lines in there. It looks fun. Alright. This is illegal. Because the Aufbau principle says we should be putting these electrons into the 1s first. Number 2, or B. Is this legal or illegal? This one right here. We start off, we put electrons into the 1s. They are both different spins. This one goes up, this one goes down. Up and down. So we're good here. And then we fill up each individual orbital before we start pairing. So this would be legal. Alright, this is a legal set. C. We start good with our 1s. We put 2 electrons in. They have different spins. Our 2s, we only put 1 electron in, and then we go to the 2p. So we should fill in this 2s before we go to the 2p. So we would call this illegal. Alright. D. So by the Aufbau principle, these are good because we filled in, it's building up. We don't have anything in the p orbital. But both of these electrons in here have an up spin. So they are sitting in the same seat. They have the same quantum numbers. So this would also be illegal. This electron here, it should have a down spin. Same with this electron here. It should spin downwards. Because they both spin up, this is illegal. Alright, moving on to the next one. Our 1s and our 2s look good. They're fine. When we get to the p, we have up, and we filled in this orbital first. We went up and down. There is nothing illegal about that. It doesn't matter which one of these p orbitals you fill in first, as long as all three of them get an electron before you start pairing, it is fine. This would be legal. And last but not least, we have our example here. Again, our 1s and our 2s look great. When we get to the 2p though, we have paired up this middle orbital before this one has gotten an electron, so we would call this illegal. Right? Next question here. Giving us the electron configuration for zinc, give me the answer. I should say in normal notation and noble gas configuration. So this one's kind of the big ticket question of the quiz, so I really want to go over this. The first thing that we need to know is this is not an ion. Alright, I just say for zinc. Here is zinc, right here. Zinc has an atomic number of 30. That means that there are 30 protons. When there is zero charge, the amount of protons equals the amount of electrons, and we are dealing with 30 electrons. So we have 30 electrons. So what we start to do is we start to fill these in one by one. Here's our first electron. 1, 2, 3, 4. Now we go to our 2p. 1. Notice the way that I'm doing this is very specific. I'm adding 1 to each one of these orbitals before I start pairing them up, like so. So we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. We have 30 electrons, so we don't have to fill in the 4p. It's empty. So our electron configuration of zinc, we're going to start with order. 1s2, because there are 2 electrons in this 1s shell. Alright, so this number here, all that means is how many electrons are in that particular subshell. Alright, 2s2. So we've done this. I'm going to cross them off as I go. We have 2p6 because there's 1, 2, 3, 4, 5, 6 electrons in this energy level. 3s2, 3p6, 4s2, and finally 3d10. So notice how we are going in the order of energy. There is a method for which to know which orbitals come first, but I'm just going to give this to you. I don't want to overwhelm you too much, and I don't think it's something that's really necessary to learn. Here is our electron configuration. I'm going to just erase this bit and rewrite it. This is a whole lot of information. Okay. All of this is the electron configuration. There is a way to make this shorter, which is known as the noble gas configuration. So here is zinc, right here. The way that you get the noble gas configuration is you go up a row. So we're in row 4 here. You're going to go to row 3, and you're going to go all the way to the right to column number 18. We're going to get the official names for all of this. That's going to be in our next chapter. But I want us to know that these are noble gases. Basically, the things that we care about are anything that's after the electron configuration of argon, which is the row above it, the noble gas of that row. So anything that is argon's electron configuration, we don't really care about. Those are electrons that they're pretty vacuumed in. They're never going to leave. These electrons, on the other hand, from this row, they kind of might leave. They matter more. So if we go back, argon, if our S is these two. Here is our 2s. Here's our 2p. Here's our 3s and our 3p. All right. So anything that's after 3p, which is our 4s and our 3d, these are the electrons that we care about. So to do our electron configuration, we will do zinc equals, we put this in parentheses, or the brackets, argon, which is anything up to 3p. This is the same as this. And then we just have, I forgot it too here, 4s2, 3d10. This is a more concise way to put this information. All right. I'm going to update the document after this with this answer. I just wanted to show you how to do it in the video. Last but not least, we have honors. The electron configuration of copper is Ar3d10 4s1. So if we actually go back to here, copper is right here. It's actually right next to zinc, so it's got one less electron. And I'm just going to show these two shells here. All right. So here is our 4s, and here is our 3d. Now these are the 5 slots in them. All right. So instead of boxes, I'm just putting lines. All right. So copper has an electron configuration that looks like this. The reason for this is having 10 electrons gives more energetic stability than having 2 electrons in the 4s. So having a full, I'm going to type this out. I'll actually just type this out here. Why this exception? So having a full D shell is more energetically stable than having a full S shell. In general, having a full or half full shell leads to better stability because it requires less energy. Especially when there are more orbitals in the subshell. So the 3D and the 4S shells are very, very similar in energy. Because of that, the energy required to get this into a quote-unquote excited state is less than the stability that having a full shell gives you. Having this full shell it's stable. You got a full house, full bus. It works much better than having one open lone pair here rather than having the lone pair over here. Okay? All right, so that is all. I'm going to type up this the last question right here. I'm going to be posting this video Wednesday night, so my 2 scholars class will have had the whole lesson. The honors class, you won't, but if you want to pre-watch this video before we actually go over the material in class, be my guest. Be my guest. Go ahead. Other than that, have a great time studying.